This section is going to revisit some ideas that you've probably remember from your Math 113 courses, the idea of parametric equations and plane curves. So parametric equations allow us to describe not just where an object has been at a given point x, y, but when the object was at that point. So we are going to introduce a third variable, t, which we call a parameter. And then we will write both x and y as functions of t, and this will give us a set of parametric equations for a given curve. So for example, it says suppose an object follows the path given by the equation y equals negative x squared over 72 plus x. If we let x equal 24 times the square root of 2t, and let y equal negative 16t squared plus 24 times the square root of 2t, we're going to determine the position of the object at times t equals 0 and t equals 1. So this is just straight up plug and chug. At t equals 0, x will be 24 times the square root of 2. And notice that the way that this is written, the 2 is the only thing that's under the square root. T is not. So I'm just going to plug in a 0, which gives me 0. Y is going to be negative 16 times 0 squared plus 24 square root of 2 times 0, which is 0 plus 0, or 0. So at t equals 0, the object is at the point 0, 0. At t equals 1, x will be 24 times the square root of 2 times 1, which is 24 square root of 2. And y is going to be negative 16 times 1 squared plus 24 square root of 2 times 1, which is, of course, negative 16 plus 24 square root of 2. So the object is at that position where x equals 24 square root of 2 and y equals negative 16 plus 24 square root of 2. At the time t equals 0, t equals 1, we have the coordinates of the object. Now this expression y equals negative x squared over the 72 plus x is what we call the rectangular equation to represent this curve, and you can see it there. The parametric equations are found here, and that's where we impose this time parameter on it. This also creates what we call an orientation, and we'll look at that in a second. You can see that there is an order of things. We're moving from t equals 0 to t equals 1 in this direction. And the path with the orientation attached to it is called a plane curve. So the definition of a plane curve, it says if f and g are continuous functions of t on an interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. The set of points x, y obtained as t varies over the interval I is the graph of the parametric equations. And taken together, the parametric equations and the graph are a plane curve denoted by c. When we plot the resulting points in order of increasing values of the variable t, we trace the curve in a specific direction, also known as the orientation. So that's what I was talking about a second ago. The orientation of the curve is this order here, this going from t equals 0 to t equals 1. This example says sketch the plane curve described by the parametric equations x equals 2t squared minus 6 and y equals 2t minus 1, where t is between negative 2 and 3. So what we're going to do is we're going to sketch the curve, and we're going to plug in t equals negative 2 to t equals 3 and just plug in the integers in between those two values, but we are going to actually plot it as a continuous curve because t could be anything, not just an integer. So I'm going to create a chart, and we're going to go from negative 2 up to 3. We're going to find x, and we're going to find y. So I'm going to plug negative 2 into both of these equations. So when I plug it in for x, I'm going to have, let's see, let's just do the x column first. 2 times negative 2 squared minus 6 gives me 2. When I plug in the negative 1, I get negative 4. When I plug in the 0, I get negative 6. When I plug in a 1, I get negative 4. When I plug in a 2, I get 2. And when I plug in a 3, I get 12. Plugging in for the y equals 2t minus 1. When I plug in the negative 2, I get negative 5. The negative 1 gives me negative 3. The 0 gives me negative 1. The 1 gives me 1. 2 gives me 3. And 3 gives me 5. So now I'm going to plot this. And we need to go at least from x equals negative 6 up to 12. So, and we need y to go from negative 5 to 5. Okay, so I'm going to have 2, negative 5. And I'm just going to make a little note that that's at t equals 0. Or sorry, t equals negative 2, not 0. Negative 2. And negative 1, negative 3 at t equals negative 1. And see, negative, oh, that should have been negative 4, negative 3. There we go. And negative 6, negative 1 at t equals 0. And negative 4, 1 at t equals 1. 2, 3 at t equals 2. And 12, 5 at t equals 3. So you can see the shape that's being formed here. It's a partial sideways parabola. And it does have the orientation that moves in this direction around the curve. The orientation is important, so make sure that you are plotting that as well. Okay. Notice that in this example we had both a rectangular equation and a parametric equation. And when we talk about eliminating the parameter, what we're trying to do is find a rectangular equation that represents the graph of the set of parametric equations. So like with this example, this is a parabola that could have been represented by just a rectangular equation. So what we want to do first is take our parametric equations and solve for t in one of them. We're going to substitute that value of t into the second equation, and then we will have a rectangular equation. So for this one, I have x equals e to the negative t and y equals e to the 3t. So I'm going to take this equation and I'm going to take the natural log of both sides so I can solve for t. And for this one, I'm going to have a negative t on the right because natural log of e to any power is just equal to the power. So that gives me t equals negative natural log of x, which I'm going to substitute into this equation. So this is the same thing as saying y equals, I can switch those two and make that e to the natural log of x raised to the negative 3 power, because you know that a power raised to a power, you just multiply the powers. So we're doing that in reverse. E to the natural log of x is x. So I really just have 1 over x cubed. So my equation here is y equals 1 over x cubed. Sometimes you'll find that you need to adjust the domain when you eliminate the parameter. So for example, with this one, it says eliminate the parameter and adjust the domain of the following parametric equations, where x equals 2 over the square root of t minus 1 and y equals 2t over t minus 1 for t greater than 1. So here I'm going to take the first equation here and I'm going to square both sides. So I get x squared equals 4 over t minus 1. And I'm going to cross multiply. This is understood to be over 1. So I get x squared times t minus 1 equals 4. And then I'm going to divide by x squared and get t minus 1 equals 4 over x squared. And then I'm going to add 1 to both sides. So I get t equals 4 over x squared plus 1. Plugging that in, y will be 2 times 4 over x squared plus 1, all divided by 4 over x squared plus 1 minus 1. That's my t there, which of course those will cancel. So I get 8 over x squared plus 2, if I distribute the 2, divided by 4 over x squared. And I'm going to do a keep change flip to multiply this by x squared over 4. So I get 8 over x squared times x squared over 4 if I distribute plus 2x squared over 4. And doing some canceling, I get 2 plus x squared over 2, or x squared over 2 plus 2. That looks a little better. Okay, so this is my y. Now to adjust the domain. If t is greater than 1, then that means that t minus 1 is greater than 0. And we know that x, which is 2 over the square root of t minus 1, because this whole denominator can't be negative anyway, has to be greater than 0. So x greater than 0, or from 0 to infinity, or 0 to infinity not including the 0, is the new domain. So we have y equals x squared over 2 plus 2 for x greater than 0. And that would be our adjusted domain. Another type of scenario that you might see is one of these where you have trigonometric functions. So for example, x equals 4 secant theta and y equals 3 tangent theta. In this case, the parameter is the theta here. So when you have a situation like this, you want to use a Pythagorean identity to your advantage. And remember, there's a couple of those. There's sine squared of theta plus cosine squared of theta equals 1. If you divide everything through by a cosine squared, you get tangent squared of theta plus 1 equals secant squared of theta. And if you divided through by a sine squared of theta, you would have 1 plus cotangent squared of theta equals cosecant squared of theta. So whichever one you have the pieces for is which one you're going to use. And in this case, we have secant and tangent, so we're going to use this one right here. So what I'm going to do is I'm going to solve each of these for secant of theta and tangent of theta. So I'll get x over 4 equals secant of theta, and y over 3 equals tangent of theta. And then I'm going to take the identity and I'm going to plug those substitutions in. So instead of tangent of theta, I'm going to write y over 3. Y over 3 squared plus 1 equals, and then instead of secant of theta, I'm going to write x over 4 squared. So I get y squared over 9 plus 1 equals x squared over 16. Or another way to write that is 1 equals x squared over 16 minus y squared over 9. And we'll talk later about how to recognize what that looks like. Now on the flip side, we may be interested in finding a set of parametric equations for a rectangular equation. So depending on the amount of information you have to use, you can either just let x equals t and go from there, or you may be given some requirements. Like this one says t has to equal 0 at the point 3, 1. So for this particular example, we need to figure out what x would have to be in terms of t to make this happen. And there's definitely more than one way to do this. So your answer may not look like somebody else's. It just has to meet the requirements that are stated. So one option, you could choose x equals t plus 3. You could see that if t is equal to 0, then x would be 0 plus 3, and this would allow that point to be satisfied. So then, everywhere that y has an x, I'm going to replace it with t plus 3. So I'll have 2 times t plus 3 minus 5, which is 2t plus 6 minus 5, or 2t plus 1. And you can see that if you did plug in a t equals 0, you would get the point y equals 1. So my parametrization here would be x equals t plus 3, and y equals 2t plus 1. Other options, you could choose x equal to, for example, 3 minus t. That would work also because when t equals 0, 3 minus t would be 3 minus 0, or 3. The only difference is you're going to have to adjust your y to accommodate for that. So y would be 2 times 3 minus t plus or minus 5 when we substitute. So we get 6 minus t minus 5, or 1 minus t, negative t plus negative 2t plus 1. So this is another option that would also satisfy the requirements. The only thing that has to happen is that your x and y have to go together. This one says to find a set of parametric equations for the rectangular equation y equals x squared, where t equals 4 at the point 416. So you have a couple of different options here. Obviously, I mean, you could say x equals t, and that would take care of it because you would have t, t equals 4 when x equals 4. And in that case, y would just be t squared. And there's nothing wrong with that because that would work. You could also choose something like, for your y equals 12 plus t. And that would give me y equals 12 plus 4, which is 16. And then you would have to adjust your x to meet with that. So x would have to be a plus or minus though, and that might be a little bit problematic because x is squared here. So that's one option, but it does, not always work exactly the way you want it to. You could also choose something like x equals t squared over 4, because 4 squared is 16 divided by 4 is 4. And y would be t squared over 4 squared, which is t to the 4th over 16. So this would work as well. The only potential problem I can see is that if you're allowing for your t to be negative, this would not cover the entire curve of y equals x squared. So you do want to be a little bit careful with letting your t be squared because that can cause a little bit of an issue with your domain.